Let's continue now with problem 415. So what I recommend is that you open the book and read the problem. But in any case, in problem 415. And in this case, we have a tank with 5 kilograms of steam. P is equal to 400 kPa. And we're going to add heat. So heat is going in. Q is equal to 85 kilojoules of heat. And at state 2, I know the pressure is 2,500 kPa, and the temperature is 700 degrees C. So it's pretty hot. And what we want to do is find out what the problem is. So we don't know what this initial state is. So we have this problem, but we're following the methodology that we talked about. So we drew a sketch. It's a closed system. The substance is H2O, is water, and the process is very important in this case. What stays constant? What stays constant is the volume, or the specific volume. So I have V is equal to a constant, or specific volume is equal to a constant. So with that, now I can, so then is energy involved? And the answer is yes, so I can write the first law. So Q is equal to delta U plus W plus delta KE plus delta PE. And so I write that there's no change of potential energy, there's no change of kinetic energy, and because it's constant volume, the work is 0. So all these things go up, boop, boop, boop. And so Q is equal to mass times U2 minus U1. So in this case, I know the mass, we were given that. I know Q, we were given that. I know U2, I can look it up. So U2, it's superheated. I have 3466.4, and I have the specific volume at 2 is equal to 0.17824. And if I look at this process on a TV diagram, down here 400 kPa, and we're going up to 2,500. And so I'm starting, I don't know where I'm starting, but I'll assume I'm starting in the mixture region, and I'm going to go up like this. So I'm going from state 1 to state 2. The specific volume stays constant. So now I could solve this equation for U1 if I wish. So I could have here 9585 is equal to M times, well, it's 5, I know what that is. Mass is 5 times 3466.4 minus U1. I can solve for U1, and U1 is equal to 1549.4. And now I have a choice. So if I wanted to find the internal energy, I could do that. I can also find the quality from this term, knowing U1. I can find it from the specific volume, which is what I happen to do. So I'll do that. So V1 is equal to V sub F plus X1 V sub Fg. And in this case, this value, V1, is greater than V sub F and less than V sub G, so it's in the mixture region. So 0.17824 is equal to 0.001084 plus X1 times 0.46 139, and I get that x1 is equal to 0.384. So I can find the quality. I could have found the quality using the internal energy. So in this case, the problem was a little bit overspecified, but it introduces the idea for constant volume processes, it's constant specific volume, and that's an important concept. Now I'd like to look at another problem. Let's look at problem 420. Again, I recommend that you look this up and read it in the text, that you not proceed watching the video until you've done that. It's your call. So 420, we have, in this case, we have a mixing chamber where we're going to have steam coming in at 90% quality, 600 kPa, and it's going to mix with water at 20 degrees C and 600 kPa. And they're mixing together and producing hot water, 2,000 kilograms per hour at 85 degrees C and 150 kPa. So we'll call this state 1, state 2, and state 3. And I want to be able to look up the properties, but before I do that, let's go through the problem-solving process that we had talked about. So it's an open system. The substance is water. It's adiabatic. There's no heat loss. And delta KE and delta PE are equal to 0. So I can write the first law in terms of enthalpies. So what I'm going to eventually do is find the enthalpies here. So energy is involved. Yes, so we write the first law. So you refer to the first law equation that we had in chapter 3. So I have Q dot plus M dot 1 H1 plus M dot 2 H2 is equal to W dot plus M dot 3 H3. And I know M dot 3 is equal to 2,000 kilograms per hour divided by 3,600 seconds per hour. And that's going to give me 0.555 more 5s kilograms per second. So what we want to do is put the mass flow rate in the consistent units for SI. And now what I do is I want to determine the enthalpy we have with the quality here. So H1 at 600 kPa, H1 is equal to 670.1 H sub F plus 0.9 times H sub Fg, 2087 H sub Fg, and that's going to be equal to 2548.4. H2 is equal to H sub F at 20 degrees C. So it's a subcooled, so this is a subcooled liquid, so we're using the subcooled liquid, subcooled. And so this is equal to 82.9. In H sub 3, there's another subcooled liquid, H sub F at 85 degrees C. It's also subcooled, and this is 356.7 kilojoules per kilogram. Now when I look at this equation, I have m dot 1 and m dot 2. So I know that m dot 3, the mass coming out, is equal to the sum of the two masses going in. So m dot 3 is equal to m dot 1 plus m dot 2. So this is equal to 0.555555, as many 5s as you want. And so I can solver this, and m dot 1 is 0.55555 minus m dot 2. So now I can substitute this in I can take this and substitute it in for m dot 1. M dot 3 I know is a number, so I have that, and I know all the enthalpies. Oh, what about the work? Is there a paddle? Is there a paddle going on in this? No. So there's no impeller going on here. It's just a heat exchanger. And so there's no impeller, so the work is 0 as well. And the heat, as we talked about, was 0. So now I have a simplified equation. .5, all these 5s, minus m dot 2 times 2548.7 plus m dot 2 times 82.9 is equal to 0.555, all those 5s, times 356.9, 356.7. And so with that, I'll solve for m dot 2 and m dot 1, and I'll write it at a higher level, so I'm not bending down to do that.